Assalamu alaikum. Welcome back guys to Engineering Geology. My name is Engineer Abid Ali and today we are gonna discuss plate tectonics. So let's get started. Plate tectonics, which is basically is an extension of Alfred Wegener work. This theory that we are going to look at was put together in the mid of 1900s and built upon that Wegener began working early in the century. So let's get started. The first thing we need to know is this: the outer shell of the earth is like, for example, we take is like being a magic shell on a scoop of an ice cream. The solid outer crust of the earth we call the lithosphere. So it's actually broken into pieces that we call plates. You see here, you can call them lithosphere plates, you can call them tectonic plates or simply plates, but this is the solid outer part of the earth that we live on. Some of the plates are oceanic crust, some of them are continental, and some are combination of the two. That's going to become important. Keep in mind that we do have these two distinct type of crust. If you look at the gray here, this is our continental crust. It's thick, it's made of rock granite. It's not quite that dense, only about 2.7 gram per cubic centimeter. But if you look at the dark gray area under the oceans, that the oceanic crust is very different. It's much thinner, more dense, because it's made of rock basalt. The density of the basalt is about 3 gram per cubic centimeter. Keep in mind that information can be found on your Earth's interior chart in your reference table. Now that crust, whether it's oceanic or continental, along with this kind of orange section called the rigid mantle, those two together are what we make our lithosphere, the solid outer shell of that. Keep in mind that beneath that is a kind of gooey plastic, partially melted bubblegum layer called asthenosphere, and so the plates that we live on are actually floating on this asthenosphere. Now beneath down in the asthenosphere, that a melty gooey bubblegum like rock is actually able to move, and it moves because of the process known as convection. Essentially, convection says that the hot material becomes less dense and rises, and then when it rises, it cools down, becomes more dense and sinks, and what we end up with are these rising and sinking currents called convection cells. In the mantle, those end up being the machine, the force that driving the motion of the plate. So in this diagram, we have a type of boundary called divergent boundary, where the plates are literally being ripped apart by the movement of the convection beneath. Keep in mind, this convection takes place in asthenosphere, right now the lithosphere. Let's take a look at the map of the plate. So it's very similar map at your reference table, which we will see shortly, but for the moment take a look at what you notice, that the plates, some are very large, are a little bit smaller, but they are all moving. What that means is that there is a lot of action in the plates where plates meet. For example, that's where we can find all our earth is shown here with the pink dots. That's where we can find all our volcanoes shown here with the red triangles, and this is also where we find a lot of the earth active mountain ranges. So keep in mind that all seismic activities, earthquakes, volcanoes and mountains tend to happen at or near these boundaries between plates, which bring us to those boundaries themselves. Now all of plate tectonics come down to the fact that things happen when two plates interact with one another. So we need to know what those interaction looks like, and it really boils down to three types of interaction, three types of plate boundaries. The first is known as transform boundary, and that occur when plates slide one past another as seen by these arrows. We also have convergent boundaries where plates collide, and divergent boundaries where they drift apart. You should be familiar with each of these and the kind of thing we see at each of them. So let's go into some example here. Okay, I'm going to be alluding back to this chart. This is a map with your reference tables that shows plate boundaries, so keep that handy as you are continuing to learn about these. Let's start with the transform boundaries. So these are the boundaries where plates slide past one another. Take a look at this animation. You will notice the lithosphere floating on the top of the asthenosphere is being driven by convection current, which is causing them to slide literally past each other, right past each other, and so right along that boundary in the middle you get a lot of pressure build up along, a lot of grinding over the plates, which is often released in the form of the earthquake. Transform boundaries, very commonly earthquake, however, they don't tend to have volcanoes, they don't tend to have major mountains, and certainly not trenches. The only real feature we see at transform bodies are earthquakes. This is example in the place of the earth where you can actually see a transform body at the surface. This is known as the San Andreas Fault, and it's found in California. It's responsible for the big earthquake risk of cities like San Francisco and LA. Let's back to our reference table for a minute here and see that the transform bodies are shown down on the bottom with this symbol shown in green. Here there's a couple of them, not too many, but the most famous and important one would be the San Andreas Fault, shown right here again. If you forget how transform bodies actually work, the arrows kind of reveal the motion, so it's a good tool to use your reference table. Next type of plate boundary would be convergent boundaries. These are little more tricky because we have to consider not only the fact that two plates are coming together and colliding, but what type of crust is involved. For example, we see different things happening when it's oceanic crust colliding with oceanic crust, and as opposed to when it's continental colliding with continental, and so forth. And so we have a few different types of convergent boundaries. The first one, we call it subduction zone, as you can tell by this little animation here. This happens when the continental crust on the left collide with the oceanic crust on the right. Notice that the oceanic crust is sinking underneath the continental crust, and that's because oceanic crust is more dense than continental crust. It's heavier, and so when the two collide, the heavier oceanic crust sinks underneath the lighter continental crust. When it sinks, it melts because it's so hot down in the asthenosphere, and that melting rock finds little cracks and to rise through and ultimately erupt at the surface, forming active volcanoes. And some of the feature we look for is subduction zones are a chain of tall mountains and action of active volcanoes, a deep ocean trench seen by this dark line just off the coast, as well as lots and lots of earthquakes which tend to happen along that subduction plate. We also have island arcs, now very similar to subduction zone. The only difference is that this is oceanic to oceanic, so no continents involved here. The one thing it's tricky is that it's little hard to tell which plate is going to subduct, being that they both have the same density, but eventually one plate, usually the older rock, will sink under the younger rock, and again we will get this melting which causes rising magma to create active volcanoes, which in this case from island volcanoes. Island because we are talking about areas out in the middle of the ocean here. We also get a trench which you can see clearly in the water there. Of course we have a lot of active earthquakes and along subduction plates. Before I go back to the chart, here we also have a third type of convergent boundary called collision zone, and that would be continental. The best example of that would be India crashing into the Eurasian plate where the Himalayas are forming. But again, convergent boundaries can be seen with this symbol down here, and probably the most famous one that we will discuss is the Peru Child Trench on the west coast of South America. So that would be an example of the subduction zone, because you notice that the Nazca plate is in the ocean, so there's oceanic crust. The South American plate is a continent, that continental crust, and so that give us a subduction zone. That where the Andes mountains are a lot of volcanoes, lots of earthquakes. Finally, we have a divergent boundaries where three plates drift, different plates rather drift away from each other. Again, we wanted to consider the type of crust involved. So if it happens on land, we have what we call a rift zone. where the land actually rips apart into two. We see this happening in Eastern Africa right now. Right now, an area known as the African Rift Zone, as you can imagine, when the rock rips apart, it allows magma to escape. So we get we get active volcanoes, we get some minor earthquake here, so that are not significant, as the convergent boundaries would be often. We will see this in the middle of ocean. We call that the mid-ocean ridge shown here. So the convection currents that are actually pulling the plates apart, then magma is coming up in the middle, forming mountains and volcanoes, and again some earthquakes. Now there's one tricky thing of this, that are actually a couple tricky kind of points. Here is one too bad, and that's the idea that the younger rock is always going to be found right along the ridge, because that's where all this magma is cooling to form new rock. As you get further away from the ridge of the rock, age will increase, it's get older and older, and as you get further from the ridge. Now here's the trickier thing, that rock when it forms, it actually records the earth magnetism. If you recall, we talk about how the earthquake is like a giant magnet, but the magnetism changes every so often, so those changes recorded in the rock. So what we can see in the rock is either side of the mid-ocean ridge are these alternating bands of magnetism which match up on either side. That's an important observation, because it's proof that the earthquake is actually spreading apart, and it proves that the divergence is actually taking place. So if we look at the reference table here, the symbol for the divergent boundaries, and again the most common one is probably the span of the Atlantic Ocean, the mid-Atlantic ridge. Right through here it actually extends all the way down south, but probably the best example, although you see them all throughout the ocean of the world. Now we do have problem here, because plate tectonics says that all volcanoes and earthquakes should happen at these plate boundaries, but if really look at the earth carefully, there's a handful of places where we get volcanoes that are not a plate boundary. And the best example I could give you, how Hawaii smack into the middle of the Pacific plate, and so the geologists have to consider this and come up for an X with the explanation. So as we have some volcanoes that weren't at plate boundaries, and the answer of these locations are hotspots. So hotspots is simply an area where we have a single area of magma that's able to punch through in the middle of the plate. So we are not talking about a boundary, we are basically talking about one simple individual solitary point where you have active magma rising up, and it rises from something called a plume. We can't predict where these will happen. We notice there's maybe a dozen of them right now. Sometimes they are very active, sometimes they are not as active. Here's how they work. Now if you look at this diagram, you are going to notice shortly a metal plume that is coming up from the asthenosphere. It's just a hot spot that the magma is strong enough to actually punch through the lithosphere to create an active volcano. But the problem is that the lithosphere is moving, because remember, all the pieces are constantly moving around, and you will get this active volcano which is then dragged to the side, making way for a new active volcano to form, and that is dragged to the side and a new one will form, and so forth. So what you end with this chain of island, if it's happening in the ocean, with one active volcano over the hotspot and then a chain of extend or dormant nor active volcano extended away from it. And what's cool about this is, if you look at where extend volcanoes are, you tell you the direction that they tell you the direction that the plate is moving, and that's pretty much in a nutshell. And the content that we need to know about for this chapter, you guys will be learning a lot of more about it in the coming class, inshallah. And I just want to do a quick review for you guys. Thanks a lot. If you guys have any questions, feel free to contact me through the WhatsApp, or you can contact me through the email. Take care of yourself, stay home, stay safe. That would be all for today.